We now start our discussion on the second module of chapter 6. We continue from where we had left in module 1. So, in module 1, the last result which we had proved is monotone convergence theorem, which stated that if Fn is a sequence of non-negative measurable functions defined on a measurable set E, and if Fn is pointwise convergent to a measurable function f, then integral f d mu over E is obtained as the limit of integral Fn d mu over E. So, we will see some of its applications first. So, we first go to our first slide of this module. So, again see the statement of monotone convergence theorem. If Fn is a sequence of measurable functions defined on a measurable set E and Fn is monotonically increasing and Fn converges to the function f pointwise, then integral f d mu over E is equal to limit n integral Fn d mu over E. So, we first see an application of this monotone convergence theorem. If Fn, n belonging to capital N, is a sequence of non-negative measurable functions defined on a measurable set E, and the infinite sum of the series Fn sigma n is equal to 1 to infinity Fn is f and it is defined on E, then we have sigma n is equal to 1 to infinity integral E Fn d mu is equal to integral f d mu over E. Again, we know that Riemann integration does not have this property. For Riemann integration, we only have the property that if f and g are Riemann integrable, then integral of f plus g is equal to integral f plus integral g, and we can extend that result only up to finite number of sums, that is sum of finite number of terms. But for Riemann integration, for infinite series of functions Fn, this result does not hold. So, we again have another advantage of Lebesgue integration over the process of Riemann integration. We will not go into the details of this proof, but just let me prove this result in this way. We first take two non-negative measurable functions f1 and f2. We already know that if f1 and f2 are non-negative measurable functions, then we can find sequences of simple functions which are monotonically increasing, say Si and Si dash, which converges to the functions f1 and f2 respectively. Subsequently, if we consider the sum of the sequences, that is the sequence Si plus Si dash, then this sequence is again monotonically increasing and it converges to f1 plus f2. And if we apply the monotone convergence theorem on all the three sequences, then we have integral f1 plus integral f2 is equal to integral f1 plus f2, because we already have proved that for two simple functions s and t, integral s plus t is equal to integral s plus integral t. Again, if we consider the sum of the infinite series f, we know that the sum is the limit of the sequence of the partial sums. Now, since each Fn is non-negative, so this sequence of partial sums is again a monotonically increasing sequence of measurable functions, each non-negative, and it converges to the sum function f. So, again applying the monotone convergence theorem, we get the desired result. We now consider another application of monotone convergence theorem, and the statement is that if Fn e to closed 0 infinity is measurable for each positive integer n, where e is also measurable, then the integral of the lim-inf of the sequence Fn, that is lim-inf Fn d mu over E, this is less or equal to the lim-inf of the sequence of integrals, that is integral E Fn d mu. Now, note that here Fn is not assumed to be convergent or anything. So, for any arbitrary sequence of measurable functions, of course non-negative, we have this particular property. We prove the assertion in this way. We know that lim-inf n Fn x is actually supremum over n infimum I greater or equal to n f I x, that is equal to supremum over k g k x, where g k x is defined as infimum I greater or equal to k f I x, and for all x belonging to E. So, how we define the lim-inf? We first take all the values f1x, f2x, f3x, fnx, etc., and take the infimum. Then we delete the first term, we start from the second term, that is f2x, f3x, f3x, etc. Since this new sequence has one term less, so the infimum increases. So, the infimum increases as n increases, and this forms a monotonically increasing sequence, and its limit we know that it is supremum. Again, from our knowledge of measurable functions, we know that if Fn is a sequence of measurable functions, then the lim-inf and lim-sup, which always exists, they are also measurable. So, here each gk is measurable, and moreover we have already observed that this sequence gk is monotonically increasing, that is 0 less or equal to g1, less or equal to g2, less or equal to etc. And obviously, the limit of gk is lim-inf n Fn. Now, it is clear that gk is less or equal to fk for all k. So, integral of gk is less or equal to integral over fk. And now, if we apply the monotone convergence theorem, then we have lim-inf over k fk d mu, this is greater or equal to lim-inf over k integral over E gk d mu, but this is nothing but limit over k integral over E g d mu gk d mu, and this is equal to integral over E lim-inf k fk d mu. So, we have the result. So, we have obtained at least two convergence theorems which are not valid for Riemann integration, but are valid for Lebesgue integration, but it is not that everything is very positive here also. So, here also we have examples of sequences of functions which are Lebesgue integrable, but their limit functions are not Lebesgue integrable, or the integral of the limit function is not equal to the limit of the integrals of the sequences of integrals f n. So, we start with one example. Suppose the function f n on closed 0 1 is given by f n x is equal to 1 by x if x belongs to closed 1 by n 1 and 0 elsewhere. Now, each f n is a bounded measurable function on closed 0 1, and we know that it is Lebesgue integrable on closed 0 1 from our discussions in chapter 5. But see that this sequence f n pointwise converges to the function f, where f x is equal to 1 by x, where 0 less than x less or equal to 1, but it takes the value 0 at x equal to 0. But this particular function f is not Lebesgue integrable. So, here we have a sequence of functions which are Lebesgue integrable, but the limit function is not Lebesgue integrable. Again, consider another sequence of measurable functions. Suppose f n is defined on closed 0 1 by f n x equal to n if 0 less or equal to x less or equal to 1 by n and 0 elsewhere. Obviously, each f n is actually the characteristic function of 0 closed 0 1 over n into a number n. So, each f n is a simple function, and so each f n is Lebesgue integrable on closed 0 1, and f n converges pointwise almost everywhere to the constant function f equal to 0 on closed 0 1, which is also Lebesgue integrable. But see that the value of the Lebesgue integral of the limit function, that is 0 to 1 f d mu, that is equal to 0, whereas each value of the integral 0 to 1 f n d mu is equal to 1. So, we have a sequence of 1 only, a constant sequence, and its limit is equal to 1, and of course, 1 is not equal to 0. So, in this case, though the limit function is Lebesgue integrable, but the Lebesgue integral of the limit function is not equal to the limit of the Lebesgue integrals of f n. Again, we go back to one of the results which we had proved for simple functions. Just recall that if S is a non-negative simple function defined on a measurable set E, then this simple function can generate a measure on the collection of all measurable subsets of E. Similarly, instead of a simple function, if we take a non-negative measurable function f defined on a measurable set E, then also we can generate a new measure by the same process. That is, if I take say nu star A equal to integral f d mu over A, then we can show that this nu star also becomes a measure on the collection of all measurable subsets of E. Now, we go to our next definition. So, again recall that if f is a non-negative measurable function defined on a measurable set E, then the Lebesgue integral of f on E is defined by integral f d mu over E is only supremum of integral s d mu over E, where s is a simple function and s is less or equal to f. Now, we have already seen that the value of this integral can be equal to infinity. F is said to be Lebesgue integrable on E if the value of this integral E is less than infinity. So, there is a difference between Lebesgue integral of a function and the Lebesgue integrability of a function. So, if we consider a non-negative measurable function defined on a measurable set E f, then always remember that the value of the integral f d mu over E, this always exists. Either it is a finite number or it can be equal to infinity. But we say that f is Lebesgue integrable only when the value of the integral is finite. So, what we did in this module of chapter 6 is that we have seen two applications of monotone convergence theorem and proved again two convergence theorems, one of them for an infinite series of functions, both of which are not necessarily true for Riemann integration, but are valid for Lebesgue integration. We have also defined the Lebesgue integrability of a non-negative measurable function, and in the next module we will see the difference between the Lebesgue integral and the Lebesgue integrability of a function. So, with this observation we finish this module. Thank you.